Very good. Let's see here. I will start with looking at the outline. So I'll go over some fundamental concepts very quickly and introduce the tribological system and a review of the first and second laws of thermodynamics, introduce entropy generation for systems in which temperature is changing rapidly and significantly, and also how we would use the Helmholtz potential to characterize such systems. And then I'll introduce the DEG theorem and give some examples of example applications of these concepts. I noticed last year that you guys had Professor Konsari from LSU who gave his talk on degradation science. So there's going to be some overlap on that content, especially as it relates to the DEG theorem. So keep that in mind. Okay, very quickly here, I put in some very simple definitions for those that may not have thermodynamics background, but for an audience like this, I think it's okay to go through this really quickly. The good thing is that the presentation is being recorded, so you can always go back later if there are concepts that you want to revise, okay? So generally, the control volume is the region of interest, which is what we're concerned with, and the system is everything inside of that region. And we will call the system open if matter can flow in and out of it, as well as energy. And it's closed if only energy can cross the boundary. And isolated is a whole different ballgame because in an isolated system, both matter and energy cannot interact with the system. For what we're going to talk about today, we will be focusing on the open and the closed system. The boundary is the interface that demarcates the limit of your control volume. So there in the slide, in the picture, you can see a visualization of the definitions. What's your control volume? What's your boundary? These are all important because when we do analysis in tribology, it's very important that we understand what region is critical or is crucial to the analysis we're doing. What are we trying to analyze? What area, what we would typically call a contact area, do we care about? So that's why these are important. What's a reversible system? When you deal with a case where the system is not changing over time, we will call that a reversible system. Or to be more specific, the system could lose energy or gain energy, but it doesn't degrade. So it stays in the same state, whether you deplete it of energy or not. The system itself is not changing. But the irreversible system will be the other side of the equation, where we have systems that do change over time. And so as you can imagine, all real systems fall under the category of irreversible systems. Our more definitions here is the concept of energy dissipation. You really will want to think about every time you have energy conversion or transfer, there is always loss of energy accompanying it. Okay, this energy dissipation is not to be confused with heat dissipation, which just refers to heat leaving a hotter body to a colder body. And generally, the energy dissipation leads to degradation of the system, as we have seen from data and experience. And continuous degradation is going to result in a sudden loss of functionality, which we would call fatigue failure. Some more definitions here, a quick example of irreversible versus reversible processes and systems, just to make sure that we're kind of all on the same page here when you hear the word reversible to understand what I'm trying to say. You probably are familiar with this concept here, and these are typically ideal cases. As you can see, ideal gas is one of those. Concept like time travel, staying young forever, no aging. Bernoulli's equation is also a really good one. There is no losses. There are no losses involved in it, and elasticity also. And on the other side, we get the counter processes where we have aging, friction, highly dissipated processes. Again, everything on this side is real, and on this side is ideal and generally theoretical. For the focus of what we're going to be talking about today, we are on this side, the real systems. Actual dissipated processes that lead to degradation and eventual fatigue failure. All right, so now that leads us to the conversation about tribology very quickly. In tribology, we say motion should be efficient and reliable. So for us to understand the fundamentals of how the machine elements work and feel is extremely important. And that leads us to the definition of tribology as the science and technology of interacting surfaces in relative motion. I personally like to define it as a branch of engineering and not really a branch of science, because in tribology, we put together everything that we've learned from other branches of science, and we try to solve the problems that we deal with in contacts and interfaces. Okay, these are two common laws in tribology that we use for friction and wear: the Coulomb law and the Archard-Wear law. Actually, here on this slide, here on the right side here, is a depiction of the trouble control volume that comes from one of the references that I've used for this presentation. All right, and then the trouble control volume essentially involves everything that we care about when we do tribology analysis. And that's what that would look like. It's the typical tribological system. It's composed of 4 subsystems. We have surface 1, surface 2, both in relative motion. So V1 and V2 are usually different. And then the environment is also important. Is the high relative humidity? Is the environment hot temperature environment? Is it a vacuum? Those all play a big role in how your interface is going to behave. And then also we can have a dry contact or a lubricated contact. So the lubricant here is in parenthesis, because sometimes you have it, sometimes you don't have it. So generally, this is what a typical tribological system is going to consist of. And it is very dissipative just by its very nature. So you guys can imagine friction is one of the most dissipative mechanisms in nature. And in tribology, friction is the #1 thing that we deal with, as well as plasticity. And as many dissipative mechanical mechanisms you can think about, we deal with them in tribology. And that means they will be highly irreversible as well, so causing significant degradation of your system. To characterize the tribological system, we need operating condition. We need to know what's going on, what load are we subjecting the interface to. So we would need to know things like normal force, temperature, velocity, and time, which we use to calculate things like the sliding distance. But we also need to know the material properties, right? Because if I'm doing analysis on a polymer, my results are going to be clearly different from if I'm analyzing a steel interface or steel and brass interface. So the materials themselves are going to really play a big role in how the interface is going to behave. So here I've listed a couple of properties, including some thermodynamic ones on this side: heat capacity, thermal expansion or thermal strain coefficient, and others. And you do the characterization, and you end up with an output, the friction and wear quantification, as well as any interface degradation taking place. All right, so how do things degrade? Very quickly, here's the first law of thermodynamics, which everyone is familiar with. I have depicted it with this picture here. On this right side, that's the first law using internal energy, which is what this here is. It's just a change in internal energy. And then here's the second law, which looks at the change in entropy, which is what this first term is. And this term here is what we call entropy transfer into or out of the system. The last term is entropy generation, and that is going to be the focus of this conversation. Now, when you combine these two together, well, that one here is the second law. So I draw a line from this one to represent this image here. You combine those two and rearrange, and you end up with this entropy generation. That's the full formulation. Now, the problem with using this at this moment is the internal energy can have all kinds of meaning in a system. As a matter of fact, a system could be degrading, but if you compute the internal energy, it could actually go up. So we have to be really careful about that. The other problem is that now I need to know how entropy is changing, and that can be very difficult to compute accurately. So then we introduce the Legendre transform of internal energy, and that brings us the Helmholtz free energy, and that leads to this format of entropy generation. And this here I have found to be a lot more consistent in characterizing tribological systems and instead systems that are undergoing external load. So we're talking about, this workshop is on fatigue. So when you're loading a component for externally, applying load on it, that also applies here. And so we would use the Helmholtz free energy to compute the entropy generation. So now I'm going to go through each term very quickly. The first term is the one that looks at the temperature rise of the system. So in a case where you have an isothermal system, that term can go to 0. But if it's not isothermal, as in real world cases, that term is always there. And then that's your boundary work, and that's your chemical reaction. So you could have in tribology, we deal with things like grease oxidation. We also deal with corrosion of surfaces and interfaces, and that would be the reaction term. And these two together are essentially the load that your system is undergoing. So they are the active mechanisms that we can measure on the system. The last term is the ideal work. So it's like looking at your system without losses or degradation. That's the ideal case there. All right, and then the next thing I did was kind of talk about what entropy generation means in general from a physical perspective. How do we think about it? For ideal systems, theoretical, it's 0. But for real system, it's always greater than 0. And it's always positive. And as such, by that very nature of it being always positive in real systems, we can use it to measure the energy dissipation and irreversibilities taking place in the system. Okay. So that same equation on the previous page, I kind of explained it in terms of regular words here. And I said entropy generation then becomes the phenomenological entropy minus the reversible one. So here's the same equation. And now I've put everything here in the square brackets. And these are all now defined as the phenomenological entropy. And that's your phenomenological path, which I will show you in a second. Okay, and these here have already been previously defined. It's the same thing from the previous slide. And that there we call the PEG theorem in a recent paper that we published. And that's the visual depiction of the equation. So you can see the purple profile. That's your phenomenological path. Okay, so that includes temperature rise, includes the mechanical work going on, includes chemical reactions. So you can think about all the possible active mechanisms you can think about for a system. They're all included there. Okay, and the green line represents your ideal path. And the difference between the green line and the purple line is your entropy generation. And that's what we're looking at here at the top with, all right, so I'm trying to change my pointer. That's your entropy generation. And that comes as a difference between those two terms. All right, so when you have, like what we're saying for most systems, most real world applications, temperature change is not 0. And for those cases, this term here cannot be neglected, the first term here. And so for those systems, you want to include your change in temperature, the MST term, the macrostructural thermal term. And that would include all high rate dissipating mechanisms, including plasticity, friction, and wear, which are very critical for us in the area of tribology. Okay, so very quickly, I wanted to quickly give examples of when we say work or generalized boundary work. I was talking about external work just now. What does that mean? So here are a few examples of what you would find in most engineering systems. I think there's somebody whose microphone is on, just like mine was earlier. Is it possible to mute that person? All right, we'll keep going there. All right, so here we see various forms of work that you can encounter in engineering systems. It's not exhaustive, it's just a few of them that are listed. And when we're looking at a tribal control volume, we care about the first 4 of them. So shear motion, where you're looking at friction and you're looking at stress loading, normal stress loading. And sometimes you can have multiple processes happening at the same time. So when we define the work, it doesn't always have to be just one of them. It can be multiple systems, multiple processes happening at the same time. In that case, you would have to add them all to get a couple of them together to get your total work done. Okay. And at the bottom here, you have electrical work and compression work, which you would find in other systems. So the entropy content, I talked about the MST term, the one that carries the change in temperature. One problem that it has is this term is why I started with how we formulate entropy generation first, because when you do that, Then to characterize degradation, all you need to do is say, oh, well, here's the degradation, and I relate it to this entropy generation and get some constant of proportionality between them. And this theorem was proposed by Michael Bryant, Marco Consari, and Frederick Ling back in 2008, after a lot of studies, of course. And that's the mathematical notation for it. There you have your degradation measure, you have your entropy generation, you correlate those two together, and you get the coefficients as your output. Okay, and that's the three-step analysis that I just described. First, you get entropy generation, you measure your degradation, or you can also estimate it if you have a model to estimate degradation of fatigue, loading, and all of that. And you correlate those two together and you get your coefficients. Okay, so that's essentially the entire premise of my discussion. Now, everything else that I have left will be applications. Okay, so first we start with the steady processes. In this case, temperature is held constant or it changes very minimally. For those kind of processes, the delta T is approximately zero. We call them steady state process. And for that to happen, internal energy, entropy, energy in general is was going to change steadily. So we will call that in thermodynamic terms, we will call that equilibrium formulation. Okay. So entropy generation is minimum. In the experiments I'm going to show next, some of them are performed at Texas, or one of them from Texas and the other one from Consari, Professor Consari's lab at LSU. Let's see, and this one here is the very first one. Looks like this. We're looking at the turbometer, and there you can see here what they've done here in the turbo control volume is they force cooled it. You have a slider and a rider system. So you have a rider and then the slider is rotating and there's boundary lubrication, very little lubrication there. And then there's a lot of forced cooling to keep the temperature constant. So what they did in this work was, if I can keep the temperature constant, then I can assume the entropy change is constant, not generation, entropy change. And then when I rearrange, I just get the entropy generation is equal to the entropy transfer by heat. So now you're flowing all that heat out by force cooling the system. And then they measured the wear, and they found out that when they correlated the wear with the entropy transfer out of the system, they found a linear correlation. Okay, I think there, I don't know, on this side here, it feels like my presentation is not working too well, but there is supposed to be a linear plot down here at the bottom. I don't know, maybe you guys can see it. Okay, and then for abrasive wear, this work here was done at LSU and Professor Kosari's lab. And again, in this case, there was forced cooling to keep the temperature minimum, temperature change minimal, so keep it at a steady temperature. And again, that leads to, okay, if I invoke the equation I derived earlier of phenomenological entropy, in this case, because they are force cooled it, now that first term can be neglected. And then in that work, all they needed to measure was friction force. So via the normal force and the friction coefficient, now you can compute minimum entropy generation, which is what has been done here. Okay. It's back on now. Can you see it?
Yeah, right.
Okay. I can just finish real quick. These are just examples of everything we've been talking about. Here is Grace Walker experiment. Again, this was done at LSU. And again, in this case here, they have kept it as pseudo-steady state so they can focus on the mechanical work on the grease. This is sharing work. So you see shear stress and shear strain. And again, in this case, we have now looked at the MST term. And again, they measured degradation, they correlated it, and they get that linear correlation between wear or between degradation of the grease and entropy generation. Now, when in cases where temperature change is significant, now that term that we've been canceling now becomes really important. For example, this work that I did during my PhD where I shared grease in a cup without cooling it, and I found out that the temperature was rising as I was sharing it. In this particular case, I had to keep both terms in there, and both of which ended up being significant. And that led to this characterization. Now I have two terms in it, and as you can imagine, it leads to a three-dimensional plot because now I have two terms on the horizontal axis, and then I have my degradation measure on the vertical axis. Okay. And for grease oxidation, we also applied it, and we had two processes taking place, and we were able to also use the same approach to characterize that. And in this case, we're looking at the oxidation induction time of the grease, and that led to a similar result. Other applications that we're currently looking into, I have some master students working on this, coffin and wall iron polymer coated sheet metal. This is a problem in the steel manufacturing industry. And then thermal degradation of grease. It's something also a study that we recently completed. And that's all I have. Again, this is the summary of everything I just talked about. And these are some references if you want to go read up on some of the content. That's it. Thank you very much for listening. If you have any questions, go ahead and ask, or you can reach out to me after the meeting with your questions. I'll be very happy to answer them. Thank you.